The simple problem that we'd like to consider is our first exposure to relatively complicated states of loading. And for this purpose, what I'm going to do is I'm going to take a sort of a toy geometry, but certainly is motivated by a practical scenario of interest. So what I'm trying to do here is draw a block which will serve as a containment for the deformation of another material. So that's our block, okay? And within that block will rest yet another one. Like this, okay? All right, good. So now, before I forget, let me also assign some coordinates here. This is x, that is y, and that is z. So I like to motivate this simple example first. And that motivation comes from a simple manufacturing operation associated with presses forming things out of sheet metal. So eventually when you do your training, you might see that into, say, a car factory gets delivered sheets of metal. These are pretty huge sheets. They're not small. They could be, let's say, they could have a diameter of 1 meter, and they could be more than 1 meter in length, several meters in length, and it's an aluminum sheet of a certain thickness, several millimeters. So what you can do is you could unroll this sheet and from that extract a sheet of a certain thickness. Okay. And what you'd like to do now is take this sheet and form ultimately, say, the shape of a car door, from which you can do some more manufacturing operations and eventually manufacture the car door and use it in assembly. So we're going to take this sheet and we want to now form it into the shape of a car door. And the way to do that is to use a die that has the shape of a car door, okay, or that shape is contained within the die. And this die will have a negative image located on a press. Okay, so that's also a part of your die. And there is a huge press here because these are metals that are hard to shape. They require enormous forces. So this huge press will eventually take, so let's say the lower portion is fixed. The press will come and close up on the sheet of metal you have and apply a stress of certain magnitude, and eventually when the press closes and opens up, this initially flat sheet will have taken the shape of the car door according to the shape of the die. Okay, so we have a sheet metal and we apply compressive stresses on it, and eventually you have the portion of the car door forming. Now in this process, obviously what we would like to have is the sheet metal deforming into the shape of the die surface and not the die becoming flat due to the pressure that is applied. So we don't want the die to deform, and you manufacture and design the die itself in that way. The whole process rests on that. So ultimately we're going to omit the deformations of the die because we're not interested in it and it shouldn't be significant. And so we will in fact idealize the die as being rigid. So here this block is going to be like the die, and I have a red material like this sheet metal that I'm going to apply some compressive forces on and try to sort of form into a thinner sheet. Of course, this process is not governed by elasticity alone, because when you remove the die, the shape remains. Permanent deformations indicates it's not elastic, but here we're just interested in the initial elastic deformation phase of this process. If the forces are not that large, deformations initially certainly will be elastic. And our goal is to demonstrate the importance of using generalized Hooke's law. So the die is idealized as being rigid. Nothing in reality is rigid, but it just means that the idealization means that the deformations of the die is negligible in this process, in this analysis, compared to the deformations of the sheet metal. And that's what the material is indicated as, okay, in this as a motivation in this example. The material properties are E and nu. I understand it to be isotropic. In reality, the die is lubricated with some surface agent or oil, so that eventually you ensure that the metal can spread on the surface easily, slide easily with little friction. And in this case, we're going to also assume that the surfaces are frictionless. Okay, one way or another, we obtain a frictionless surface. Now, friction for a given normal load with respect to the surface, normal load has to do with normal stresses. Friction has to do with the tangential direction. So if there is no friction, there is no tangential force. If there is no tangential force, the normal force is there and hence normal stress. No tangential force means there is no shear stress. So frictionless assumption eventually will induce the outcome that there are no shear stresses in this example, hence there will be no shear strains. So that's our simple idealization. We're only concentrating on the normal components. And eventually, the type of loading we have is through a stress, sigma z. I both indicate the direction and I give the value as sigma z clearly because it's compressive. Sigma z has to be negative. The sign is important. It has to be embedded within sigma z. Okay, so we can say sigma z is a certain compressive stress of magnitude sigma naught, let's say. That's okay, but when I say it's sigma z, it has to be negative something. Okay, we understand that to be compressive. And this is a rigid die. There is a material that fits tightly on the surfaces, and I compress from the top, and I'm gonna try to now determine the answer to the following questions. Question number 1. What is the stress in the y direction? B, what is the strain along the z direction? And C is a similar question. What is the strain along the x direction? And finally, D, let me first phrase it, and then eventually when we solve the problem, it will become more apparent. It asks for the ratio of sigma z over epsilon z. Now, normal stress over normal strain. Under normal circumstances, this would be the Young's modulus. But now we are considering generalized Hooke's law, going a step beyond uniaxial loading. We will have multi-axial states of loading, multiple normal stresses present at the same time. We'll have to use generalized Hooke's law, not the standard one, and therefore we're going to denote the ratio as E prime, which already indicates possibly that this is not going to be equal to E. That's why I'm indicating as such. Okay, so this is sometimes in words called the stiffness along the z direction. Okay, now let's go ahead and proceed with the solution to this problem. And the solution ultimately will rest upon the generalized Hooke's law. And generalized Hooke's law is the first thing, therefore, that we need to write down. And we have to know this relation by heart. And it's really not hard to remember the relation at all. It's always 1 over Young's modulus. Remember the units. This is units of mega or gigapascals, Newton per meter squared in the end. And then that scales the stress of the same unit. And then epsilon x is 1 over e, stress in the corresponding direction minus nu, the Poisson effect in other words, composed of minus nu times sum of the stresses in the remaining two directions. That's a simple way to remember the normal stress-strain relation in the generalized Hooke's law. So it's 1 over e, stress in the corresponding direction y, minus nu, the sum of the stresses of the remaining two directions, x and z. And then epsilon z is 1 over e, sigma z, minus nu, sum of the stresses in the remaining two directions, sigma x plus sigma y. Okay, so we've written our generalized Hooke's law, and now I'd like to go ahead and apply it. And the question is, well, find sigma y. Well, first of all, before that, let me ask you a simpler question that is easier to observe. Epsilon x, what is it? Well, I go ahead, I'll check epsilon x. I assume I know e, I assume I know nu, and I am given sigma z. It will have a negative value like minus 50 MPa. I know sigma z. Well, but what is sigma y and what is sigma x? Unless I know these two, I cannot determine epsilon x, right? And likewise, I cannot determine epsilon z, and so on. So it seems, first of all, I have three equations in terms of three unknowns. So that's a well-defined set of equations. But I am only given one value explicitly, sigma z, for the right-hand side. And I need to know sigma x and y somehow to determine epsilon x, epsilon y, epsilon z, or I need to somehow have some balanced combination of three equations and three unknowns. Presently, I have only one known, sigma z. So here is where observations come into play. So in these types of problems, there isn't a single straightforward way to solve the problem, not always at least, but the observations should be stated, in my opinion, at the outset so that you can figure out the best way or best approach to the solution of the problem. So the first thing we can observe is the strain along the y direction. The material is being compressed, and I am going to implicitly assume, of course, in my analysis, I have to assume something that Poisson ratio is greater than 0. But what if it's less than 0? Just for conceptual purpose, let's discuss that, right? But metals, sheet metals are going to have a positive Poisson ratio. I know that from my knowledge of orders of magnitude. So let's say it's going to be 0.3. So when I press from the top, this thing is going to try to expand in both directions. Okay? But it will not be able to expand along the y direction because it is restricted with rigid die surfaces along that direction. So there is no room for expansion, which means that epsilon y has to be equal to 0 from the outset. So that's my first observation. So I can immediately set epsilon y equals 0. Why? Because the die has rigid surfaces. Now then comes the following question. If I have a plane with normal, let's say in this case z, and I press on this surface, well, then I impose a force per unit area on the plane with normal z, so there will be a sigma z. But if I don't do anything, this surface is called a free surface. It's a concept that's going to pop up again and again. And on a free surface, because I have no force, I have no stress, the normal stress will be 0 on a free surface. On a free surface, there is not going to be any frictional or shear stress either. But here I'm concentrating only on normal stresses, and I see that here I have a free surface. There is no constraint on that surface in terms of deformation. It can freely expand without any resistance, so it's a free surface. And because it's free, I understand immediately that sigma along the corresponding direction, the normal stress, sigma x, is equal to 0. So therefore, I know that sigma x is going to be 0 in all of the relations that I have written here. So that goes out of the picture. So all of a sudden, I am left with a setup where I had three equations for three unknowns, okay? And I have now, well, in fact, right, let's go back and count once again. I have three equations, but I had 1, 2, 3, in general, 4, 5, 6 unknowns. So 6 unknowns, 3 equations, and now I have additional information on the unknown. So first of all, sigma z is also given. That's a given of the problem. One more equation. Sigma x is now observed. Another equation, and epsilon y is also observed to be 0, another equation. So 3 strains, 3 stresses, so 6 unknowns, 3 equations from material behavior, isotropic linear elasticity, generalized Hooke's law, and 3 more inputs, one of which is already given, the other 2 I observe. So now it becomes a well-defined system of equations, and I can go ahead and solve immediately. Now, the first thing I can do is I can go ahead with part A. And part A solution is going to come from here. Part A asks us, well, what is the value of sigma y? Okay, I am sorry. Let me quickly rephrase that. Part A answer is going to come from this equality. And it asks, what is sigma y? Well, epsilon y is 0, multiply both sides, it's irrelevant. So sigma y is going to be nu times sigma z. Okay. Then part B is going to come from this equality. It's asking us what is epsilon z. Well, epsilon z is equal to 1 over e sigma z minus nu sigma y, which is nu sigma z. So it's equal to 1 minus nu squared over e sigma z. Okay, and then I can immediately go to part D and skip C for a second. I can go to part D and calculate the ratio of sigma z to epsilon z, which we are calling E prime, and it's equal to E over 1 minus nu squared. I'm going to interpret all of these results in a second. And finally, we can go to the very first one, which is going to give us the answer for part Z. We're trying to determine epsilon x, which is evidently equal to 1 over e minus nu sigma y plus sigma z, and y is nu sigma z. So we have epsilon x is equal to minus nu 1 plus nu, so minus nu, and from here we have 1 plus nu over e sigma z. Okay, great. So these are the results. Now in these types of problems, either numerically or conceptually like this, it is actually rather easy to make mistakes. So I think it's always useful to always step back and think about whether our results are meaningful or not. This is sort of a habit we should build in mechanics all the time. So, and for that matter, in any analysis in mechanical engineering. So here, first we should think about whether the results make sense or not. So we are applying a stress along the z direction, and it is compressive. As a result of that, the material tries to expand along the y direction, but it cannot. So there are restrictive stresses on the vertical walls, which cause sigma y to build up. Now, therefore, the value of sigma y, should it be positive or negative? In other words, should it be tensile or compressive? Now, the answer is that it should be compressive. So sigma y should have a negative value because the stress component, when I indicate it explicitly with directional indices, has to incorporate the correct sign. So nu, with all of my discussion, the fact that I'm assuming expansion, etc., nu is assumed to be positive, sigma z is negative, and hence sigma y is negative. So I can put sort of a conceptual check on that. Now, my conceptual check doesn't mean that the calculations have been carried out correctly, but at least I don't seem to have an outstanding mistake at first sight. Then I can think about the value of the strain along the x direction. Well, I'm pushing, tries to expand, and it's free to expand along the x direction, so I expect a positive strain. Do I have a positive strain? Positive, positive, positive values. Negative together with a negative makes positive, so I have a conceptual check there as well. And then epsilon z, well, I'm compressing along that direction. I expect epsilon z to be negative. It's going to get shorter along that direction. Negative, this is positive. How do I know that? Because nu is less than 0.5, and therefore this whole thing is also negative. It checks. Now, finally, this is a interesting outcome. Now, at the beginning of the course, if I had asked you that question, what's the ratio? You would probably say that's equal to the Young's modulus. But now we see that as a result of the multiaxial state of stress, we have the ratio coming out to be not E, but E over 1 minus nu squared. And I know that this is a quantity that's larger than E because this is less than 0.5. Now, how large is it? Let's say this is 0.3. 0.3 squared is 0.09, so it's of the order of 0.1. So this is 0.9. E over 0.9 is roughly E. So it's not a huge difference, but for sure it is larger than E. Okay, so this is larger than E. We said that this is less than 0, this is less than 0, and this is greater than 0, which are our conceptual checks. So, well, does that make sense? It does make sense. So, because what you're doing is you have a block of material. Suppose there was no rigid block that was constraining the motion of this material. And if I press on it, it expands in all directions with some degree of freedom. And the ratio of sigma z to epsilon z along that direction is a measure of that degree of freedom. But now if I constrain it in one direction and I push again, then I am restricting the ease with which it deforms along at least one direction. I'm restricting it along this direction in this case, or let's say in that direction I push. It cannot move along the y direction, and therefore restricted degree of freedom is observed. And when you restrict something, you increase, if you like, its stiffness, and that's what's happening here. The stiffness with respect to deformation along that direction is observed to increase as a result of restrictions along other directions on the block. So here I'm restricting deformation only along y. If I had additionally restricted along the x direction as well, then you could estimate that the stiffness would increase even further, okay, than this value. So, and that's what eventually indeed happens. You may want to go ahead and calculate that quantity. Okay, so all of these results seem to make sense to me, so I'll put a check here as well. Again, doesn't mean that my results are correct. In this case, they are, of course, but the conceptual checks just check the central facts without the quantitative aspects. So finally, let me ask you the additional question. What happens if nu is less than 0, or if it's equal to 0? Now, if nu is less than or equal to 0, some things do change and some things don't, okay? So, first of all, the relations as I have written it don't really care whether it's greater than 0 or less than 0. So, first of all, if nu is equal to 0, sigma y is 0. Because if nu is equal to 0, the material will not expand along the transverse directions because nu is minus nu transverse over longitudinal strain. So there is no expansion, and so I don't expect stress to build up along the y direction. So nu is 0, sigma y would be equal to 0. Okay, so this part I have written after our analysis, so here I'm not gonna put any quality sign, okay? And if nu is equal to 0, I would not expect an epsilon x either because the material is not displaying any transverse strain expansion, and if nu is 0, indeed epsilon x again will come out to be 0 in that case. Again, I'm not putting any quality. So this is still correct, this is still correct, and similarly, this would be correct. In that case, epsilon z would be sigma z over E, and epsilon prime would be, again, exactly equal to E. And does that make sense? Yes, because if nu is equal to 0, this part is omitted, epsilon z is sigma z over E. So we're back to the standard setting as if it's uniaxial, okay? And indeed it's uniaxial because there are no other forces building up. Okay, but what if it's less than 0? What happens in that case, right? Now, in that case, I have to change my observations. First, you should recognize the generalized Hooke's law is valid for any isotropic linear elastic material behavior. And nu, therefore, can take values all the way between -1 and 0.5. So the relations themselves are always valid. But what will change is the observations. When nu is negative, when I press, the material will try to contract. As a result of that, it will free itself of contact with the vertical faces that have to do with the y direction. In other words, it will free itself, meaning sigma y would be 0. And consequently, because I know sigma y is equal to 0, instead of setting epsilon y equals 0, I would set sigma y equal to 0. So I switch this 0 observation from epsilon y to sigma y, and conceptually I will then still be able to solve for these equations in terms of the unknowns that I am trying to, towards the unknowns that I'm trying to determine. So the value of, in this particular example, nu, whether it's negative or positive simply shifts this observation of 0 from the strain to the stress along the y direction, and everything else, all the steps are still dictated by generalized Hooke's law.